Okay, should be hopefully the same thing. Everyone can see it.
Yes, we can.
Yes. Okay. So yeah, welcome. I think that's already been done. But my name's Dominic Hewitt. I work at GeoVille here in Austria, and I'm part of the Earth Observation Innovation Unit, so more of the technical stuff. And Alex, I'm not sure if you want to introduce yourself now, since you'll be presenting a little bit.
Sure. Let's do it right now. That's fine.
Yeah.
Thanks, Dominic. Yeah, hello everyone. My name is Alexander Kreisel. I'm also with GeoVille in the climate department. I'm a project manager here, and I'm basically responsible for managing the crop part, but also other parts of the CopPhil project on the GeoVille side. And yeah, very happy that Dominic will take over the main part of this presentation and really guide you through the crop Earth observation, crop monitoring, and solutions. How EO can help with crop detection. Back to you, Dominic.
Thanks, Alex. Exactly. So we're going to do a quick oversight or insight into Earth observation. I know that a lot of you might have some experience and some not, so it's not too in depth, but I hopefully cover everything sort of to get up to speed there. Then we'll have a short introduction into the Senfostat system, which is what we're using to do the crop mapping, and everything from preparation through to prediction. And this uses primarily the random forest algorithm. So we'll do a little bit of background on that. So it's always good to understand what or how the program is making these predictions, so you understand more about why the results are how they are. Obviously, a big part then of crop mapping itself is about the in situ data and the sample selection and how it's prepared. So we'll have a section on that. Then a quick short, it's called a demo, but it's more just some slides just to get a better idea of how it works. I mean, it's always, you always have a vision, you think it's quite complex, but we'll break it down into just a few steps in that section. And then finally, the results and how to interpret those. So not just the classification map, but also the result figures and other things. So, okay, it's a bit slow. All right, so just a quick intro. So remote sensing, what is it? Basically, it's collecting information from another location, so a remote location. We're concentrating from satellites, looking onto Earth, but another example could be simply a camera. It's taking information of what you want to take the photo of, and you're from a different location, even though it's much closer in this case. So some benefits from this is it's spatially explicit, so we can cover the whole area all at once. And you can also get to inaccessible areas, so any kind of marshland, mangroves, just some islands. You don't have to worry about doing a campaign there to check what's there. We can all do this all at once through remote sensing. The disadvantages of this is there's limited information, so it's just what the sensor can see and what we can ascertain from this information. So obviously it would be much better if you could go there and see for yourself what's there and really concur what's there. But again, that's not always ideal, and you can't go everywhere, especially for large areas. So yeah, we can again, use remote sensing. So there's uncertainties with that, with limited information, and therefore potential for misclassification. On the right is just a map we recently did for a project called GHG Kit. This was for land use and land use change. So not crop mapping. There was crops in it, but these were grouped together, so quite coarse, into just 2 or 3 crop type groups, I would say, and the rest was land use and some land cover. So just an example of its usage, and we did that over the whole of Austria for a time series over a few years. So I just put this in. This is a depiction of the electromagnetic spectrum, so the full spectrum. And so we're not limited just to the visible spectrum, which we're used to for photos, video, anything we use where we look on a screen, so normal sort of media photos. We can also go beyond that. And for vegetation studies, also agriculture, we use a lot of infrared and red edge, which is just outside of the visible light for us. And we also use radar a lot for agriculture, but also water mapping and things like this. And this is far further down the spectrum. Let's see. This one is just to show that light from the sun, because of its temperature, its output is strongest in the visible spectrum, and that's the reason why plants have evolved to use this light, and also why we see in this spectrum. Then, yeah, I just wanted to show on the right-hand side, just quickly, the radar frequencies. There's also some satellites with different bands within this radar frequency. And the different bands are generally used for different applications. And the difference is the longer the wavelength, the more it penetrates the vegetation or whatever might be on the surface. And then important for vegetation studies is the bottom, the small one on the bottom. So it shows what part of the spectrum that vegetation absorbs and reflects. And you can see the blue, green, and red on the left. I'm not sure if you can see my mouse at all. Is that possible?
Yes, we can.
Yes, we can.
You can. Perfect. That will help. Yeah, so you can see the blue, green, and red spectrums. The vegetation tends to... Sorry, someone needs to mute. Thanks. The vegetation tends to absorb in this red, green, and blue bands, but it reflects a little bit, or it absorbs a bit less of green, and that's the reason why it is green to our eyes, because it's reflecting this. It's also reflecting a lot more of the infrared, but we don't see this. But sensors such as Sentinel-2 can, and so that's why these two bands, actually red and infrared, are really important for vegetation studies. And later on, I'll show you. It's the next slide. So we can see why it's important for vegetation. Not only can you tell then vegetation from urban or something very obviously not photosynthetic, you can also tell the difference between the health, let's say, or the condition. And that is because you can see on the left, so it doesn't, healthy vegetation really doesn't reflect much visible light. And what that would be, and that 8% would be the green band. But it does reflect a lot, or 50% of the near infrared. And then as soon as it's browning, let's say, not as good condition, let's say, then it reflects a lot more of the visible light and not so much, still a fair bit of near infrared, but definitely a difference. And so we can see on this graph, so you've got the bands on the bottom like before, you can see as soon as the vegetation is not green anymore, then it starts reflecting, and you can see a lot more in the red here, and a lot less, much less in the near infrared. So when you're comparing the two, it's quite easy to identify when you use these bands of the red and the infrared. It's often also used, especially in crop management, but not so much crop mapping, but I just thought it'd be interesting for health and sort of tracking the health of the crop. It's very important. You want to be onto it as quick as possible. So there's often a red edge band, which really goes over this line here of the vegetation, depending on the species. And this changes because of the angle. As soon as the vegetation shows that there's something happening, or it's changing, or it's you know, there's a lack of water, stress is the word I was looking for. This changes quite fast, and so just a small change in the frequency that this occurs, you can see stress quite quickly. I think that's all that's really required for this graph. Yeah, we'll move on to just a quick mention about the two different types of sensors, at least in satellites. There's the active and passive. So active is sending out its own source, light source, or electromagnetic source, whereas passive is taking it from another source, which is usually the sun. And yeah, perfect examples are radar from Sentinel-1, or all radar is sending down a pulse and then retrieving that pulse again and seeing what it is. And Sentinel-2 is the most commonly used because it's free and its resolution and revisit time, which I might come back to later. And this relies on optical light from the sun. So therefore, this one only works during the day, whereas radar has potential to run at night also. Just a few slides now then on the sort of following the process through. There's a bit of processing after we get the sensor gets some information. The first one would be atmospheric correction. So there's effects of scattering and absorption of the light by the particles, so the gases, aerosols, and the water vapor in the atmosphere. And there's a whole lot of inverse modeling and a lot of calculations to go into that to account for it. So to take the measurement called top of atmosphere and convert it to bottom of atmosphere, which is the surface, which is what we want to have the information on. And then the other one is geometric correction, which is also can be quite tricky, especially for us here in Australia. We've got a lot of mountains. And so this can cause distortion, also just from the Earth's curvature, and also the angle and the motion of the satellite. All these can play a part into making it difficult to represent what's really on the ground at that location. And yeah, there's a bit of an example on the right there, showing not only the angle that you have to compensate for, but also when there's mountains, it can even sort of shadow what's behind the mountain. And also because of the angle of the sensor, it can end up that the top of the mountain is also in a location from the sensor's point of view as the bottom. So it can really skew things. So yeah, that's another way, big step in correcting the data. And then this one was kind of just to hone in on Sentinel-2, which is Copernicus satellite. there's a few. First, there was a few examples. There's a Sentinel-1, which is radar, which is active again, sending out a pulse. And then there's another one from JAXA. It uses a different band, another radar. And then there's the two most popular free ones at the moment are Sentinel-2 and Landsat. And yeah, so Sentinel-2 is the one that we all use most often, and yeah, it's also the one that Senfostat, is based around, or developed around. And then I've got the bands for Sentinel-2 on the bottom, and it just sort of shows the gray in the back is sort of not what I thought it was, atmospheric transmission. It's basically how easy it gets through the atmosphere, and you can see these troughs is where the water vapor really absorbs. I think it's called the water absorption bands, where they really these bands don't even get to the surface. I wouldn't say, maybe I'm not sure if they don't get there at all, but they're absorbed a lot by the atmosphere, where there's not much information unless you're looking for that. So that's why there's a band 10 in there, but that's more for atmospheric studies. And we use generally the red, maybe sometimes blue for water, and infrared, as we saw, that's important for vegetation. So we use that quite a lot. And yeah, on the right is simply just the bands, the actual wavelength where they are. And again, we use often 8, 4, which is red, and sometimes even sort of the shortwave infrareds, which are a bit longer, actually. What's next? Okay, yeah. So we, after the correction of all images, so radar on the right and Sentinel on the left, we end up with a raster of digital image, and they're made up of digital numbers, and it's usually between 0 and 255, at least in this this example here. And so this is how we can imagine that a raster is built up with these numbers. And then you have different bands. Normally in a photo, like a normal photo that you look at, you have RGB, which is red, green, blue, which would be, this is Sentinel image, and this is just a true color, they call it. And then on the right side, we have different bands in the place of one of these bands. So not just red, green, blue, there might be some other bands. I'm not sure exactly what these two are on the left, but I'm quite sure this one would be including infrared. This is like a false color image, specifically for sort of vegetation identification. So you can see the infrared would have been put there probably in the red band. So this red is really striking to show photosynthetic activity. And then the rest is obviously something else. You can see the whites. Whites are more urban, and then there's sort of bare soil or lower cropland scattered around the other areas. And then radar exactly is the same. It also has digital number. And this is just, it's called the backscatter, which is basically the reflectance, except it's not visible light. So we refer to it as backscatter, and how much of that comes back to the sensor. And it is referring more to the texture of the ground. So it's not so much the color, it's the texture of the ground. And you can see the water is quite dark because water absorbs radar. And so it doesn't get reflected back, and so it gets a low value. Yeah, and I won't go too much into radar because we don't actually use it for Senfostat at the moment. It's a feature that might come in later. Yeah, so the reason I brought up the numbers is because from those we can make combinations or indices, and this can help condense information to something that's really important, similar to this RGB, this false color here. So we can, it's used really to show the vegetation. It's quite easy then to identify it. Similarly, we can make these indices. So the most common one that maybe everyone's heard of before is the NDVI, which is a normalized difference index, the vegetation index in this case. And this gives a value of between -1 and +1. And you can see in the bottom right, this is an NDVI image. Yeah, and you can instantly see sort of the green areas would be forest or cropland. You can see the areas that have been harvested as well. They've got a very low value, and you can see also the river in the top left over here is quite low, and that would be because there's no vegetation. Then I just threw in a few examples to show that there's hundreds actually. There's quite a few indexes or indices because it's quite common for your use case, whether it be looking for burned areas, for harvest areas, for a multitude of things. You can develop your own index. You can experiment and see which one really, maybe has a better linear relationship or something with a certain variable you're looking for. So yeah, the relative greenness index is just built upon the NDVI, sort of to compare between the highest and lowest values in the area. Vegetation difference is, again, another one just to look at the time difference, so between one day and the other. I think D was for day. And then another one, well, it's not completely different, it's quite similar. It's exactly the same formula as normalized, as NDVI, so normalized difference. So it takes the two bands, one is minus over one plus the other one, which is the same as NDVI, but a different band. So I think NDVI is, red is 4, NIR is 8A, or maybe just 8. And in this case, it goes up to 12. So the shortwave infrared, which is actually longer than near infrared. So it's using infrared and a longer wave infrared. And here we can see NBR on the left here. This is in Turkey on a recent project we did. And we were looking for burn areas. And so we decided it sounded right. We didn't develop it. It's already quite established. It sounded like the right one to use. And yeah, it really showed this burn area just after the event quite well. And then, yeah, another example is you can also make an indice out of the difference. So the before and after, which is simply, if it was 0.8 and then it was 0.5, then you just take the difference. And this can also give some valuable information. So then we have this image. We can do two things. We can classify directly on this one image, but this gives a chance that, it might be a time of the season where something isn't growing or something is harvested, or multiple reasons. There's a flood somewhere, anything. So the idea, or what we do often, is create a time series, and so you capture this, any changes, and from this we can also extract time series information or annual information. So here I've just got an example saying 90th percentile of NDVI. So if for one pixel you took it in a season where nothing was growing or was even bare soil, that's not really obviously representative, and you're not going to be able to predict the crop type from that. So having a whole time series of information doesn't limit you to missing information like that. And also cloud cover, for example, if you're in a very cloudy region, or it's commonly got cloud, then you can still get some information in the end. And that leads me then again to the time series, and more specifically to the crop mapping. So you can also find some information from crop phenology. For example, here on the left, yeah, I've shown how you can sort of extract the start of season, SOS, and end of season, EOS. And this can obviously be quite valuable information when you're trying to differentiate between different crops, which you can't get from a single image. So that's highly valuable. And then on the right is actually one of my colleagues is working on potatoes, and so this is a real world example of a field in Belgium, I think. Yeah, so we can follow the time series over the season, and we can also just quickly make a prediction of when in this case it's emergence, but it's I guess start of the season in many cases, and also senescence. When the plant is senescing, obviously it's in this case it looks a bit late, but this is just the one field. But yeah, as an example. And finally, then sort of this is quickly showing the whole workflow. Then so you have the in situ data. You can see down here. This is just a base image of true color image in the background, just showing the different classes of cropland and the polygons of the samples that were taken. Then with that information, so the ground truth and also the Sentinel-2 time series information. So like 90th percentile NDVI or start of season, for example. Then we can make a crop cover map or crop map, and you can see, that some of the information, say between the blue and the red, so these are different crops, but likely from a true color image you wouldn't be able to see that, especially just one. So we can really differentiate a little bit better there. And I think that was it for the intro to, sorry, lost my words, Earth observation. And that's it. And I'll pass on to Alex then.
Thank you very much, Dominic. Yeah, I give you some time to breathe. Maybe if there are any immediate questions right now, I think we can also take them. Otherwise, there was this previous training done already for the land cover, where there was also a quite extensive section on the general application and introduction into Earth observation. So feel free to also have a look there. But yeah, if there are any questions here, please come forward. No, that's all right. That's also all right. We also have other parts of the presentation where we make a quick stop and also give you the chance to ask questions. All right, I will just quickly introduce the Sen4Stat on a quite high level, organizational. So Dominic will then of course go more into depth on the technical part. The Sen4Stat, you can already move to the next slide. The Sen4Stat, it stands for Sentinels for Agricultural Statistics. It's an ESA project, and it was actually not developed by us. So contrary to the other land cover or the other EO services that are provided within the CopPhil projects, like the benthic habitat, the forest mapping, the land cover mapping, and the ground motion, which were all developed by the respective partners in the consortium. The Sen4Stat was actually, it was decided to use or to implement an already existing system, which was developed by the Catholic University of Louvain CS Romania, CLS, who is also part of this consortium, and the University of Madrid. And it's actually a still ongoing project. So they have a quite a very solid product already, but they are still continuing with development and improvements and updates. And this project itself, it was created in a user-driven way. So it was not. They were in collaboration and in exchange with use case countries. So more specifically with Spain, Senegal, Malawi, and Ecuador. And in those countries, with the respective counterparts, mostly the national statistics offices, but also other ministries like the ministries of agriculture, to really develop a customer-tailored approach that is valuable for the respective countries. So that being said, it's an open source solution, so it can be applied everywhere in the world, but it can also be used by everyone in the world. So it's free for download. Everyone can download it. Of course, it's not so easy or straightforward to set up because it's quite a comprehensive system. But technically, it's widely available and to be used by everyone. Next slide. So and the main goals of this Sen4Stat project are the following key objectives. So most forwardly to support the SDG reporting, among those especially the goal on zero hunger, of course, and to increase agricultural productivity. We have one that is what they call the spatial disaggregation. So there's other projects or other solutions that are applicable worldwide. Another ESA project is, for example, the World Cereal, but this is a global data set, so produced globally everywhere. Contrary to this, the Sen4Stat is also allowing to produce data on smaller areas like national level, regional level, even local level. So really breaks it down to the local situation. But for this, of course, it needs in situ data, and Dominic will get more into detail on this later. But this is really a strong argument for this solution, that it allows you to go further into depth on more specific locations within the country, because the world is, of course, very diverse with many different crops and agricultural products. So and can give you, even on very specific area types, it can give you a good information what's on the ground. Then we have also the estimated timeliness, of course. So with Earth observation, you have imagery available every 3 to 5 days, which is quite a dense, information network. And it also allows you even to forecast, certain parameters. It's not so much a focus of this project, but technically it's also included in this overall package that is offered as a service. Then, of course, also said already, cost efficiency. So instead of going into the field everywhere all over the country, you can use satellite data from your offices. It's available in a very dense time series, and you can exploit this data in a quite cost efficient and fast manner. And then we have also to reduce the uncertainties in the survey data. So there's it's a more objective use of data, of course, because it's algorithm based. So there's no margin for, or little smaller margin for human error. And the data is coming in a standardized way. So this Sentinel data is always the same tiles over the same area, usually in the same time frequency. So the gaps between images is usually the same. Of course, can also happen that there's sometimes not an image available, or there's the problem with cloud coverage, but generally it's quite reliable data set that you can working with. Okay, next slide. So overall, the key technological aspects that are really the core argument, or the strong leg of Cent4Stat is to provide data in a 10-meter optical cloud-free synthesis. So by using Sentinel-2 in a very dense time series, they provide different spectral indices, especially for vegetation and biophysical variables. Dominic already mentioned a few. And then, of course, the outcome is a 10-meter crop type map that you can modify basically, or yeah, you can modify it to your own demand. So crop type really means that whatever you tell the algorithm through the input data, it will give you back. So it can be either a very specific crop type map from maize, tomatoes, and rice, for example, up to aggregated data sets like annual versus perennial crops, or even a very comprehensive just crop extent map. So everything is possible depending on what you're seeking for and what you are providing as an input data, so the algorithm can learn with it. And then there's two more parameters or variables that the system can technically offer, but we are not focusing on this within this training or within the CopPhil, but as said, it's also part of the package. So you can also still continue with this if you're interested in this, which is large scale set of crop growth metrics. So yeah, to really predict and to see to get yield estimates as well on different variation aggregation levels. So which is especially important for the statistical offices and agricultural departments. And I think that was the last of my slides. Yes, so we'll hand it back over to you, Dominic.
Yep, thanks. All right, so yeah, as I mentioned earlier, the main algorithm that's implemented at the moment with Cent4Stat is a random forest algorithm. So we thought it's best that we explain or go into a bit of detail of what this is, what it means, how it works, and this understanding can help understand what to expect from the algorithm. That's not the right button. No, it's too far. So I'll start with decision trees. So I'll explain the difference in a minute. But so a decision tree is quite simple. So it takes all of your data from the top, and it's basically always splitting the data depending on a feature. And so some people explain it as like a yes/no question. Is it above this or below this? And you split it. And ideally, it's or you find the best way to split it. And ideally, that's putting classes, separating the classes, let's say. So you have all your data in the top up here, and you ask a question, for example, the NDVI, so the 90th percentile, it's not the max, but it's the high end of the scale, and we say, for example, is it below 0.5? And then yes, we split it off, and most of the green ones in this case go here, and no, these ones are mostly red, but there are still some green ones. So if we want to further split that, then we take another feature, or the same feature even, and we split it in the best way possible again. In this case, I don't know, let's say it's something from the crops. So start of season, and we have a day of year, and we split it above this over here and below this over here, for example. And so this is referred to as, or here it's referred to as growing the tree. And you can go as deep as you want, as far as you want, until you've split your data into the different classes. And then when you want to make a new prediction, so we have a data point that it hasn't seen before, we've already got this tree set up with the threshold, so we put it in and it goes, okay, it's above 0.5 here, and the day is quite early, so it goes over here, and this is how we make a prediction. As mentioned here, feature importance, we generally put the most important feature up to the top, because that's the easiest way to split that large amount of data, and then as you get further down you can refine it, and you don't have to use all features. Sometimes you can use the same feature twice straight away, for example, just a different threshold. And I should also mention that usually it's good practice to split the data into training and testing. So you do a split. It's common to do a 70-30 split or even a 60-40 to train with some data, and then you use the test data to see how it actually performed. And so the good thing about this is it's quite easy to understand and interpret. It can deal with nonlinear relationships. You can give it a mix of numerical and categorical data. You don't have to do any data wrangling beforehand. And also for the missing values, you really don't have to compensate or anything for that. The cons of the single decision tree then is it's prone to overfitting. So as before, I was saying you can go as far as you want. You can limit that. And in general, a decision tree tends to really fit to that data that you give it to. And then when you give it something it hasn't seen before, it can be erroneous. And also, yeah, it can be biased when it's got imbalanced data. So if you give it 1,000 samples of one class and 10 samples of another, this can also cause issues or biasing. Yeah, the one on the right is actually one that I made during my studies. I can't remember the program that I used, something SPS maybe, or MATLAB, maybe MATLAB, I'm not sure actually. And you can see the splits. The first one, the most important one, was this Korean land cover. Then we used that is the median temperature or median temperature of July, for example. And this one was obviously, I also didn't design this, so the algorithm itself decided on this feature importance and where to split and all of this. So we don't have to worry about these settings. You can tweak them a little bit, but generally this is part of the algorithm itself. And you can also see altitude was also used here. And so this was the model that you would pass the new data through and see which class you get to. And the bottom left is, I just wanted to quickly show how random forests can be useful in some cases more than linear regression, which is often overlooked sometimes, but can be useful. But in this case, this is not a real world case. I mean, it's quite obvious line here, just for illustration. But it can show that, yeah, that a linear relationship or way to split the data here is just not ideal. It's splitting this class completely in two almost, whereas a random forest would follow, in this case, this not real world case, would be perfect. And yeah, I should sort of explain that this is another way to visualize a random forest, at least in the 2D. So there's one feature on the bottom that you would say it was NDVI. We would split it at this point, and we would draw a line through here. So what that looks like. And then this is another feature, the second feature, and the same thing. You would split it. Apparently here is a good spot, and so you draw a line, and that's when you get your different dissections. So finally, the random forest is using multiple decision trees. Also it can be referred to as ensemble method, because it's using multiple models for the one prediction. So in this case, or in the case of random forests, each tree would be trained, but on a different subset of the data. So because I mentioned before, it tends to overtrain, or what was the word I used? To overfitting, that's one. So if we give it data different data every time, it will possibly, not always, but it could possibly give then a different prediction. So we normally do it for, I think the standard is like 200 trees. It's a standard sort of starting point. And then we basically just take a majority vote, or each tree is like voting on the final class. And so then it's much more robust to this overfitting and reduces the effects of overfitting. And yeah, that's random forest. And so the random comes from basically using a random subset of the data each time, just specifically to reduce this overfitting problem. And that was all for random forest. Does anyone have a question at this point? Nope, that's fine. So then I'll move on to the in situ data. This, as Alex already mentioned, that it's quite important, and it's also yeah, we also had a section on it here because we want to stress the importance of knowing what to expect, let's say, from the data you put in. So yeah, high quality data, high quality training samples, sorry, are essential for accurate land cover classification. There's an old saying, adage, it's not that old, it's machine learning adage, that they say garbage in, garbage out. So no matter how advanced your algorithm is, if it's, you know, a ChatGPT model or something, similar language model, or a simple random forest, yeah, if you give it false information or not enough information or something like that, we can't expect it to learn any relationships or see any patterns in the data. It's also important to spatially distribute your samples. Having multiple samples in a homogeneous area or a block is prone to higher order correlation, and therefore, yeah, poor representatives. So obviously they are good representatives, but they're all basically considered the same. So the different crops over the geographic locations will be slightly different, whether it's the soil type or the wetness or the irrigation or management practices. These all can lead to subtle differences, and it's always a good idea to sort of account for all of this. And I'll show you later with the actual classification map, sort of what this issue can cause. Yeah, and I guess no, I'll explain it later, I think. So third point is the classes, and this is also what Alex was kind of hinting towards. The classes, they need to be comprehensive enough to meaningfully cover the potential classes, but also all groupings. Yeah, I should mention. Yet also to be distinct enough to be separated. So you want to have classes for every potential class, and basically, so if you, I'll just give an example. If you have a whole map of this AOI even that's shown here, if you just give it the algorithm in situ data for rice and corn, just two crops. To put it simply, then the prediction will classify every pixel as corn or rice, and obviously that's not correct. It's not what you want. There's other crops in there. There's also different land covers, as in urban forest things. So what you want to do is you want to cover all of the different classes. But also, if you group it into, say, an other class, you still want this other class to be distinct enough. Otherwise, if you have water bodies, grassland, forest, and urban, this is quite a broad class, and this is going to cause confusion. And so if you have a plot that is rice, let's say we know it's rice, it's quite similar to grassland. And if that's in the other class, but it's not the same as the samples you gave it, so it's rice, but it's a little bit different, it might end up classing that as something else. So yeah, trying to kind of paint a picture of it's important to cover everything, even if you're not particularly interested in it. And that's why I also brought up masking here, because, say, for cropland, we don't really care about forest areas. So we have a mask from our partner that have already produced the forest extent. So it could be the case that we don't really mind if the algorithm just says this grass, this forest area is maize, for example, because we will reclass it anyway. So that's another option. And so, yeah, I just wanted to explain that it's often an iterative process, so you can't always know how something will go. If you've got enough samples or spread out samples of, for example, maize, and so yeah, we can run it once and then see the problems, and then we know, okay, we need more samples or better samples for this. We need to maybe merge these two classes because there's too much confusion, but they're really the same. Can't think of an example right now, but yeah, some crops that we've decided, okay, we'll just class them as one because actually they're in the same category for reporting, for example. Yeah, just an example. Yeah, so I think I can also explain. So these samples, you can see these ones are, if I've forgotten now. So I think rice. I think these are rice samples, and these are likely maize. I think we're over here. Yeah, I think this is maize or onion. And you can see they're quite close. They're bunched up quite closely together. So that means that the rice up here is probably very accurately mapped. And also here, the maize or the rice, or both, it's accurate in the area where it's similar. Oops. But when we get over here, there's quite a bit of confusion because that is classed as forest. And I know this was forest here as well. And I think even this little triangle was forest, correctly classified. but there's been some confusion over here, and that would be because our rice samples, assuming, I'm not sure if it's rice over here, I don't have any ground truth over here. But whatever it is, so it's say it's rice, our samples weren't in this area, so it might be somehow a bit different. And it's different enough that the algorithms decided, maybe it's forest in this example. So that's just an example how we would need to fix the rice samples. So either get more data, better to get more data and in another location, or even better would be the location that there's problems, but that's not always possible. I think that was all for that, but still, yeah, very big. There's only 2 slides, but quite a big point to make there. So how are we going for time? Yeah, quite good. Then, so this quick demo, just the steps to get there and how Cenfostat helps us with that. So yeah, these are the main steps. So you've got the AOI preparation, so that you prepare an actual shapefile and upload that. And you also specify the season. So it depends. You can just do a month, and it takes the data from a month. You can do a year or 6 months if you prefer. Then the system itself sources and downloads and pre-processes the satellite data. So this happens automatically after you upload an AOI. Then we have to prepare in situ data and upload that, which is the most manual step in the whole workflow. And then once that's done, we can run the crop classifier, and then that extracts the information for all the in situ data parcels, and yeah, it trains the random forest and predicts and yeah, outputs a classified map. So just, yeah, some quick snapshots. They're not always the whole process, but the main part of the workflow, or the windows that pop up as you're doing it. So the AOI, just to prepare that, it needs to be a shapefile, zipped in WGS84, and then we just upload it. And I think I don't have the next slide. So here's just showing how we add a new site. So we give it a name, we upload the zip file, and then it even shows it. There is, I think, a possibility just to use, so that the program itself has a way that you choose the country, and I think even provinces from, I'm not sure what database, because we just obviously just use our own, and these are 2 Sentinel-2 tiles, it's just for testing. And then you would save it, and then once it's saved, you can go to edit and then define the site name. No, it's already done, but the season start and end, and a few other things, which I don't think I ever, no. But that's, yeah, relatively straightforward. And then it will trigger the download and pre-processing of all the data. So while we're waiting for that, then we would, oh, maybe we've already done it. The in situ data, there's two files that need to be created. One is the actual geometry, so the shapefile with the parcel ID. And in this case, the segment ID can be the same, but that I think is required as a column just for the program. But yeah, if we just keep it the same, it doesn't cause any issues, and that's used for other things. And then this parcel ID needs to match the actual tabulated data in a CSV. And here we've got the crop code that's used from Cenfostat. They have quite a comprehensive list. I'm not sure where it's from. I'm pretty sure it's constructed from other input data. And then we have quite a few columns that is required by the algorithm, or that, sorry, the program, but because we're only doing the crop type, we can just leave it blank. So that's, yeah, planting date, harvest date. The year is required, yield estimates, yield method, and quality, and the others are not required. But yeah, the columns need to be there, and that's something I will iterate over in a more practical session. And then we upload that. Yep. So then you would have this site where you're editing the season here. You would click on upload, make sure we add it to the right season that's defined, the year, and then just the two files we just looked at. So the shape files, I think zipped, I'm pretty sure, and the CSV. Then, yep. So then you just go to, it's called the dashboard tab, choose crop mapping in this case, fill out the thing that have job name, just so we can identify it if we're running more than one. The site name is the one we just uploaded before. Same season. Schedule is just, it can be automated to be done. I don't have much experience with this, but yeah, it can be automated to be done on a schedule. But we just leave that as once, and that is the default, which is always the current time that you are now, and then save it, and that will trigger it straight away. Once it's triggered, it will, as I said before, do the data extraction per parcel, and then train the random forest and make a prediction. Again, is there any questions on that? I think not. Okay, then the final section, but it's actually also important, is the interpreting of the results. So one, and the main result that everyone will be interested in, obviously, is the classification map. And you remember from the random forests, each tree, in the forest was voting. And the classification in the end is obviously whatever won this vote. And that's important. Actually, I would mention it better later. But that's, yeah, just a thing to note. Another output we get is the confusion matrix. So the reason that this is important is because that's where we get our accuracy metrics from. We calculate it from this, but it also gives a good insight as to what was labeled correctly, which is the diagonal, the darker colors, and it can also help you identify the falsely labeled classes and what they were confused with. And that's why it's quite good, and also why it helps with this iterative process. Yeah. That's all for that. And then also you get as an output the accuracy metrics. So there's, in this case, they call it precision recall, which comes from the machine learning background, but it's also known as omission commission error or user and producer's accuracy. Yeah, so the precision, I like to think of as it's referring, it's from the perspective of the reference data, which is just the points, the sample points, or the polygons, I'm sorry, often it's polygons, and just the test data, so not the one that was used for training, just the one that is separated for the testing. And so from the perspective of these points, we look how often the correct class was assigned. And this is different from recall because it's from the prediction perspective, so the whole map, and how often that was correct. And a quick way that I kind of understand it best, and in a crop sense, is if we have a small, let's just say a hectare of, or yeah, a few little parcels of cropland, say 10, we're just concentrating on this area, and we have, say, 3 polygons in there that are test data, and the whole area we mapped as corn, even though everything is not corn, we mapped it as corn. When we look at the reference data, it says, yep, that's right. Like right here, I'm corn. That's correct. But when you look at the prediction of the whole area, you see that not everything's corn, and so the recall will be a bit lower there. I hope that makes sense. So then the F-score, which is commonly used as a metric, is just the combination of these. And then the kappa, which I didn't include, I see now, is a single value. So the others are per class. The kappa is a single value for the whole model and the whole classification. And this is again the agreement between the predictions and the actual labels, but it's adjusted for random chance. And then 1 would be perfect agreement, and 0 would be simply random guessing. So it was just random chance, and there's no real relationship. But that's often not the case, except for again input data. And finally, we end up with a confidence map as another layer, as another output. And this shows the probability of this most likely case. So what the trees were voting on. And so a value of 1, that would indicate that every tree, or 100% of the trees, voted for that single class. And then on the opposite end of the spectrum, normally you would expect it to be 0, but it's not. It would be the number of classes, or 1 divided by the number of classes. In this case, there's 7 classes, which would equal 0.14. So if there was an equal amount of trees voting for each class, so each class got the same amount of votes, which would be the most confusion you can get, then the highest class, which is all of them in that case, would be 14%. So that would be the lowest possible. And you can see on the map down here that there wasn't a case where it was that confused, but still quite close, 0.25. And so we can see by visualizing the map, the higher values of the forest here. So the samples that we took for forests were good enough, and also it's quite easy to distinguish forest from other classes. And then you can see as we get into the cropland that it gets lower and lower. And from this, we can kind of start working out what classes we need to fix. And it's obviously here, not the forest class. And then, so on the right-hand side, I found a good example of a really low confidence field. And then just a true color image to show what it looks like, and the classification to show what it was classed as. And you can sort of see, because there's a few patches in there, that it is indeed confusing, because there's a mixture of classes. And yeah, so we can see, or what we can take from that would be it's low confidence, so it's most of it is forest, which is not true. We can see that. And it's maybe going to be maize because some of it was classified as that. So we probably should look at improving maize and then run it again with better samples as a something to take from this confidence map. And I think that's all we have.
Thanks a lot, Dominic. So, questions. I know it's of course always a bit more challenging to ask in front of a larger crowd, but also feel free to just put any question in the chat if there are any. Dominic already mentioned that, of course, this is the first of 3 courses actually. So this was a theoretical course. We have touched quite a bit already on topics that will be, of course, deepened then in the practical course. The practical course will be then also in person. So we will be traveling to the Philippines and we'll meet you face to face, and then also go through more into detail. You can also try and test things out. And then there's also the application course. So the next course is sometime towards end of May. And then we have also one the application course just before the Space Week in August. So we will develop and go further in depth on the further use. Yeah, the offer to ask questions is still open, but yeah, I see Carla is also already switched back visible. So yeah, feel free to ask anything or to write in the chat. In the meantime, I think I can already hand over to Carla to explain something further.
Right,
Thanks a lot for.
Yes, so thank you, Alex and Dominic, for that insightful presentation. So now we have seen like an introduction on how Copernicus data and tools like Send4Stat can be used to support crop monitoring in the Philippines. So to continue just this discussion from crop, would like to introduce you to the CopPhil Moodle, or now it's called Digital Campus. So to everyone who's attended this training session, you can get your certificate of attendance by having this account on the CopPhil Digital Campus and finishing the 2 assessments there. So one is going to be a training feedback form survey. So it's just a few questions to evaluate the whole training session. And then just a few quiz assessment items. So after finishing these 2, you can get your certificate. So I'll be sharing my screen. So here, putting it on the chat. Yes, so thank you. So Christina sent the link on the chat for the CopPhil Digital Campus. And you see here the splash page that we have this introduction, and then we now have this available courses. So if you've been following the CopPhil project, we had the introductory courses way back from October, November, and then we had the first focus into the EO service course, the land cover monitoring fundamentals course last month, February. And then now we've started with the crop monitoring. So as discussed, so this main topics will have a 3-part course, and now we've attended the first part. So introducing this platform to you, you need to have an account. So you need to create an account. So for me right now, I'll do a login, and you will see this kind of splash page for you now. So my account is just a little bit different because it's an admin account, but you will have here a short tour of the parts of the CopPhil digital campus and here, and then you can navigate through the courses. So here we can access the crop monitoring fundamentals course already. And here you can already see like the course description. So what Alex and Dominic has already discussed, and like the learning outcomes, the agenda, and most especially the slides is also already available here. You can download them by clicking on this button or also this link. And then for the other parts, there's going to be an upload of this video recording that we're having right now. And then here, as an extended material, we've already linked Send4Stat. So if you want to dig deeper into this tool, there's already some links for some resources here. And again, the important part for the certificate. So we invite everyone to walk through this platform and then finish the training feedback and then the quiz. And then after finishing both, you'll be eligible to export the crop monitoring certificate from your account. So yeah, if you have questions, just let us know or drop on the chat or just email us from like the previous correspondences. So yeah, we look forward to your participation here also. We'll now make the whole course page available to you. So some parts here are still hidden if you've visited this course page before the lecture or this training session. So all good. And yeah, if you're still having questions, please we still have some time here. But otherwise, I give back to Alexander and Dominic. To everyone, you will have access to the slides in the digital campus, and you find all our contact details there if you have tried Send4Stat for yourself or like other parts of the lecture today, and you can find the contact details of Alex and Dominic. But yeah, any other things? Alex and Dominic, we're all good.
I think from our side, it's all good.
Mm-hmm.
Yeah, I know it's getting also late in the Philippines. So yeah, if there's no more questions, yeah, as Carla said, you can also, of course, reach out to us anytime via email. Thank you very much for your attendance. And yeah, looking forward to also see you sometime in the next month in person in the Philippines for the next workshop sessions.
Yes, so to everyone, I will keep you updated in the emails for the next sessions, so you can follow us through. And yeah, see you all online and or on site for the next trainings.
Carla, there's one question actually now in the chat, which is I think a quite good question. Maybe I don't know if Marion is online, because yeah, how are the participants? How can they check if they are eligible to participate? So do they need to register somewhere? Because we do have a certain room size, right?
So on our side, so the question is when will the hands-on training take place, and how do we determine if we are eligible to participate? So if you're invited already, like receiving invitations from us, then you're already within our CopPhil stakeholder list. And based on our logistics setup, our initial plan is to open some slots for different institutions. And if you're not invited online due to logistics reasons, then the course will be again recorded, and it can be mainly accessed through the digital campus. So that's the case. So we try to accommodate everyone on site based on what's available, and then if anything else, it's always going to be on the digital campus. So okay, so for crop monitoring, the part 2, right, Alex, is going to be on site, and then the part 3 is online. So we're setting something early May or late April for May, right? May for the on site of part 2 of crop, and then to also invite you on the other CopPhil EO services. If you're also interested on learning the other services, we'll all send the invitations for the other upcoming courses, and a lot of courses will be more on site by July. So for July, it's gonna be land cover, ground motion, benthic habitat, who's having their on-site trainings in the Philippines. So also to look forward. So yeah, we will update you on the correspondences.
Great, thanks, Carla. And I think the second question was if it's also if there's a live online transfer. But I think this we need to check, right? So if it's possible to also dial in from the internet. But you will be kept posted on the further events once we're approaching it. But it's towards the end of March, I think, around the week of the 23rd, I believe, but to be confirmed.
Yes. So thanks for this question. Other things from my side, we'll keep you all updated, and like also follow us on like LinkedIn, and also we have the CopPhil website for other news. So yeah, we'll all keep in touch.
Great. Thank you very much again for your attendance, and looking forward to see you next time.
See you all next time. Thank you, everyone.
Have a good afternoon.